All right, we've spent the last several videos talking about oxygen nucleophiles. Now we're going to move on to nitrogen nucleophiles. So under mildly acidic conditions, and I bolded mildly because we're going to talk about how important the pH is for these reactions a little bit, an aldehyde or ketone can react with a primary amine to form what's called an imine. So we have to be careful with our pronunciations. We have amines and imines. And an imine is characterized by a carbon-nitrogen double bond that's part of a larger organic molecule. All right, so just like we did with the oxygen nucleophiles, we want to look at the mechanism. And again, I'm going to break it into two parts. So this is the whole mechanism, but I'm going to break it into, there's a total of 6. I'm going to break it into 3 and 3 steps. So the first 3 steps of the imine formation are the same first 3 steps as in the acetal formation, but they occur in a different order. In the case of the acetal formation, we went proton transfer, nucleophilic attack, proton transfer. In this case, we're going to go nucleophilic attack, proton transfer, proton transfer. And we'll talk about why we have this difference in a couple slides. So in the first step, the amine attacks the carbon of the carbonyl group, and the pi bond becomes a lone pair. So this is very similar to the nucleophilic attack in the acetal formation. It just comes first as opposed to second. We then get a proton transfer, and in this case, when we have the HA+, this is almost certainly the ammonium ion of the amine that we're using in the reaction. And then we follow it up with another proton transfer to get rid of the positive charge on our product. And that gives us this intermediate, a carbonyl amine. All right, and then the last 3 steps are also kind of similar to the last 4 steps in the formation of an acetal. In fact, the first 2 are identical. So we want this OH to pop off, just like we did when we wanted to form the acetal. But because the OH is not a great leaving group, we need to protonate that guy. Where again, this is probably the ammonium ion from the amine that we're using. That converted the OH into something that is now a good leaving group, so it will pop off. We now have this carbon-nitrogen double bond, and the final step to form the imine is another proton transfer, where this is almost certainly the amine that we've been using. So the differences between the mechanisms of the formation of an acetal and an imine is really due to the nature of amines. And amines are relatively good bases. And so when we're in acidic conditions, the base is going to be protonated to form the ammonium ion. And then the problem is when we form this ammonium ion, it's not a strong enough acid to then protonate the ketone or the aldehyde. But it is acidic enough to transfer a proton to the negatively charged oxygen after the nucleophilic attack. And so this is why we have the differences in the mechanism, and it's the potential presence of these ammonium ions. And as we'll see on the next slide, it's also the formation of these ammonium ions that make this reaction so sensitive to the pH, and why on the very first slide I said that this reaction will occur under mildly acidic conditions, and so we have to be careful of the pH. And so the reason we have to be careful of the pH is because if the pH goes too low, right, if it's too acidic, then all of the amines will be converted into their ammonium ions, and because those aren't powerful enough to protonate the aldehyde or the ketone, and they're not good nucleophiles, the reaction shuts down. On the other hand, we do need to have some acid present to form some ammonium ion so that it can act as a proton donor in the next step. So if the pH is too high, then I don't have enough acid present to effectively catalyze the reaction. So the sweet spot of the pH for these reactions is in the 4.5 to 5 range in order for these reactions to be effective. Okay, up to this point, we've been talking about primary amines. When we have a primary amine, we form an imine. When we have a primary amine, there's only one R group, and there are 2 hydrogens, and so I'm able to form that carbon-nitrogen double bond. In the case of a secondary amine, I only have the 1 hydrogen, and so I can't form the carbon-nitrogen double bond without losing one of the R groups. And so instead, we form a double bond between the carbon and one of its carbon neighbors. And this compound is called an enamine. So when we have a primary amine, we form the imine that has the carbon-nitrogen double bond. When we have a secondary amine, we form this enamine, where we've got a carbon-nitrogen bond with a neighboring carbon-carbon double bond. The mechanism for the formation of an enamine is identical to the mechanism we learned for the imine, except for the very last step, as we'll see on the next slide. So I'm not going to break this up into different steps. The first 3 steps are all identical to the formation of an imine. We have this same intermediate. Just like for the formation of the imine, we protonate the OH to make it a good leaving group. The leaving group comes off. In the case of the formation of the imine, there was still a hydrogen left on the nitrogen here that we could pull off and make the double bond between the carbon and the nitrogen. In this case, the nitrogen's got no more hydrogens to lose. So for the final proton transfer step, we're going to steal a hydrogen from one of the carbons that's neighboring to the carbon with the CN double bond. And so when the base steals that hydrogen, it becomes a double bond here, and this bond ends up as a lone pair to give us our neutral product. All right, so just to emphasize the difference in this last step, again, this is just the last step of the mechanism. When we're reacting it with a primary amine, our product is an imine, because I have that extra hydrogen to lose, and so I can make that carbon-nitrogen double bond. When I have a secondary amine, I've already lost this 1 hydrogen earlier, and so I don't have an extra hydrogen here, and so it's got to remove a hydrogen from a neighboring carbon atom, and so we get the double bond not between the carbon and the nitrogen. All right, so I've got a couple of examples of these in the next video.